The Galois counter mode GCM was released as a NIST recommendation for a block cipher mode of operation in the NIST special publication 838D back in the year 2007. Conceptually, GCM is a counter mode to encrypt the data and a hash-based approach to then provide authenticity to a coupling of the ciphertext and the associated data provided. The GCM mode of operation is then defined in Chapter 7, with the authenticated encryption specified as pseudocode in algorithm 4. This algorithm is specified to work against an underlying block cipher with a block size of 128 bits, to take an IV, a plaintext, and associated data as input, and to return a ciphertext and an authentication tag. The algorithm is then defined to consist of 7 steps, where the first step is to encrypt a 0-bit string with the underlying block cipher. The second step is then to prepare the 128-bit counter for the counter mode-based encryption of the plaintext, which takes place in step 3. In steps 4 and 5, the hash-based authentication of the ciphertext coupled against the provided associated data takes place. And in step 6, the final authentication tag is calculated by encrypting the hash calculated in the previous steps, and finally the authenticated encryption returns the ciphertext together with the authentication tag calculated in step 7. This sounds very interesting, so let's get started with implementing this in Python. To drive the implementation of the GCM authenticated encryption function, I fell back onto the official GCM test vectors as publicly provided by the NIST Cryptographic Algorithm Validation Program. These GCM test vectors come along as a single huge text file, and the first test vector I chose is the first test vector in this file, describing the test for GCM with using AES as the underlying block cipher. Furthermore, it's a test with a 128-bit key for AES, a 96-bit initialization vector, and a 128-bit authentication tag to be calculated. The test is clear. Given the key, the IV, the plaintext, and the associated data, the implementation has to calculate the ciphertext and authentication tag expected by the test vector. For this test, the plaintext and associated data are empty strings. The next test vector I chose to be a random test vector with a non-zero plaintext and non-zero associated data, which I found on line 19,417 of the NIST test vector file. The last test vector I then chose was a test vector with a non-zero plaintext and non-zero associated data as well, but this time with a large 1024-bit IV. This test vector I chose because of the GCM authenticated encryption specification triggering a special calculation for IVs that are not of length 96 bits, as we will see later on. Creating a dummy AES-GCM encryption function, returning an empty ciphertext and an empty authentication tag, then made all the three test cases fail as desired. Having the stage set with this driver, I then proceeded to start implementing the AES-GCM encryption function. The specification of this function is found in the NIST publication in chapter 7.1 and provided as pseudocode in algorithm 4. Like with many other implementations, my aim was to have the Python implementation very closely resembling the specification, which makes clear that this implementation is an implementation for educational purposes and very likely not fit for real-world usage purposes. Step 1 was to encrypt the 128-bit 0-bit string with the AES block cipher and the provided key, whose result is captured in variable capital H. For this, I made use of the AES implementation I created in a previous lesson. Step 2 was then to prepare a pre-counter J0, then later used to derive the counter for the countermost-based encryption of the plaintext into the ciphertext. If the IV is 96 bits, the pre-counter J0 is the IV with 31 0 bits and a 1 bit appended, with J0 to then be a 128-bit bit string. If the IV is not 96 bits, then the IV is appended with enough zeros such that this leads to a bit string whose length is a multiple of 128 bits. This is then appended another 64 bits plus the length of the IV encoded into another 64 bits. This is then hashed down with the ghash function into a 128-bit string. In step 3, the plaintext is then encrypted into a ciphertext with a counter mode-based encryption GCTR that will run on top of AES, and where this GCTR makes use of the counter resulting from the 32-bit increment of the previously calculated pre-counter J0. The calculation of the 32-bit increment function and GCTR I delegated to other yet-to-be implemented functions. In steps 4 and 5, a hash on a combination of the ciphertext and the associated data is calculated with ghash. This combination of the associated data with the ciphertext makes use of various 0-bit strings, such that the ghash receives a bit string whose length is a multiple of 128 bits. The hash calculated by ghash is then captured in variable s. In step 6, this hash is then encrypted with GCTR into a ciphertext, and this ciphertext then constitutes the authentication tag. This authentication tag is then truncated into the specified authentication tag length by taking the necessary number of most significant bits. In step 7, the ciphertext and the truncated authentication tag are then returned. Left to implement at this stage are the hash calculation ghash and the counter mode-based encryption function gctr. These are quite substantial algorithms, and as such, they will be dealt with in the next lesson.